So we're going to start with an exercise. Oh boy. So I want you to write down a number. Before you do, now you could choose any number in the world, but it will be a lot easier for you if you choose a number between, say, like 3 and 10. And if you choose a whole number, not like pi or the square root of 7 or something like that. It'll be nice if you choose a whole number between, say, 3 and 10. But what we're about to do, we'll work with any number in the world. So, have you written down your number?
Yes.
You better do what I say. All right, no. Okay, so you wrote down your number. Now, what I'd like you to do is add 1 to that number and write down the new number that you get. Let me know when you're done.
Do I write +1?
You don't have to. You could probably do this in your head. This is but yeah, I mean, you could if you want. It is up to you. You'll see what we're doing in just a second. So okay, add 1 to that number and write down the new number. You got it? So now take that new number that you got and subtract 2 from it.
Okay.
Okay, what number did you get? What was your final number that you just got?
7.
7. Okay. Now, here we go again. Start with that original number that you chose. The very first number that you chose. Take it, subtract 2 from it, and write down the new number.
Okay.
Okay. Now add 1 to it. What number did you just get?
7.
Is 7 equal to 7?
Yes.
Right. Okay. Now, why does this work? We're gonna let's see. What did we do? In the first time, you took a number, yeah. Then you first added 1 to that number. That gave you a new number. And what I'm going to do is go ahead and write it like this. This is what you did, right? And so you took your number, you added 1, and that gave you a brand new number. Now, after that, I told you to subtract 2. So then you subtracted 2, and you got your final number, which was 7. On the other hand, what I did, or what I told you to do, was you take your number. First, you subtract off 2. That gave you a new number. And so I'm going to think about it like that. That thing, after you did that, is a brand new number. And then you took that number and added 1. These 2 things happen to be exactly equal, no matter what number you start off with. And well, one way we could think about this is what we're doing here is this in this case, because the parentheses, technically we could drop them. Over here, symbolically, we could also drop the parentheses, and we have this right there. There's a couple ways we could think about this, but the thing is, addition and subtraction are commutative. We could, when we're only talking about addition and subtraction, or I chose subtraction in this case, we could have done addition and addition, or we could have done a subtraction and subtraction. And technically, if we think about this, subtraction is addition, right? Like subtracting 2 means the exact same thing as adding a -2, right? Subtraction and addition are actually the exact same thing. It's just we call plus -2, we call it subtract 2. But at any rate, the point is that addition can be done in any order we want. It's commutative, right? +1 - 2 is the same thing as -2 + 1, right? So this operation commutes. I could do this and then do that, and it means exactly the same thing, right? Okay, so nothing new here. I'm just beating a dead horse at this point. Now, okay, here we go. Get ready. Pick any number. If you want, you should take your original number that you started with, whatever it was. Take that original number, add 1 to it, and write down that new number.
Where'd it go?
You can choose a new number. It doesn't matter. It's not the point. So if you want, you can choose a new number, write it down.
Okay.
Okay. So you have your number that you just chose. Now I want you to add 1 to it and write down the new number that you get.
Wait. Again?
Wait. Okay. Starting over. Pretend we haven't talked about anything yet. Let's start from the very top. Choose a number and write it down.
Okay.
Okay. Now add 1 to that number and write down the new number that you get.
Okay.
Okay. Now take that new number and multiply it by 2.
Okay.
What did you get?
18.
18. Okay. Now take that original number, that one that you just wrote down, the very first one, and multiply it by 2 and write down the new number that you get after multiplying it by 2.
Okay.
Okay. Now take that new number that you just got and add 1 to it. What did you get?
17?
Uh-huh. Is 18 equal to 17?
No.
No. And let's see why this is the case. Okay. In the first instructions I gave you, I told you to take your number, add 1 to it. That gave you a new number. Okay. And so we're thinking about whatever's in the parentheses is my brand new number that I got after I took the original thing and added 1. Boom. Then I took that number, whatever it was, and we multiplied it by 2. Okay. On the other hand, we said you take your original number, you take that same number that you started off with, multiply it by 2. Okay. So we multiply it by 2 first, and then we add 1 to it finally. And let's just kind of look at this. We're wondering, are these the same thing? And it turns out that they are not the same thing. We saw this with an exact case that one's 18 and one's 17. But let's take a look at this. This is 2 times the quantity x plus 1. So the 2 would have to distribute in. And that would give us 2x plus 2. On this side, we only have 2x plus 1. And indeed, this is 1 more than what we started off with, but that's not really the point. We're not going to get into the ins and outs of that. But it turns out these are not the same thing. There's no way these could be the same thing. 2x would cancel 2x, and I would subtract 2x from both sides, and I'm left with 2 equals 1, which is not true. That's never true. It's never the case that 2 equals 1. No matter if we're on Venus or if we're in some alternate dimension. Well, I don't know about alternate dimensions. I can't talk about that. But as long as we are in creation as we know it, 2 does not equal 1. And therefore, this will never be equal no matter what number you started with. Doesn't matter what number. Why? Well, because addition and multiplication do not commute, right? And by multiplication, I mean multiplication by a whole number or by a fraction, right? So the same way I said that addition and subtraction are actually the same thing, that subtraction is just the addition of a negative number, division is just multiplication of a fraction. Like I could take x and divide it by 4, but that means the exact same thing as take x and multiply it by 1 over 4, right? So what I'm saying is addition and subtraction are really the same thing, just they're disguised a little bit. Division and multiplication are the same thing. They're just written a little bit differently. But the big point, the big takeaway here is that while addition commutes with addition, you could do that in any order that you want. It turns out, and also ditto with multiplication, You could do multiplication in any order that you want. If I say, take a number, multiply it by 3, then divide it by 4, you'll get the same thing as if you first took your number, divided it by 4, and then multiplied it by 3. The division multiplication commute, that's perfectly fine. But then when we mix these operations, multiplication and addition, they do not commute. You can't do them in any order. What I'm getting at, and this is kind of the theme of today, is that order matters. It really matters when we mix together addition and multiplication. And so we're going to have to keep that in the forefront of our brains. Just like, and this is something we've seen before. You don't need to write this down. It's just, you know, if we had something like this, 2x plus 1 equals, say, I don't know, let's do 3. If we wanted to solve that, we wouldn't, I mean, we could first divide by 2. It's going to be ugly. But if we're thinking about this the way that we've been doing this, is we kind of say, well, what's the first thing that happens to x? First thing that happens to x is he gets multiplied by 2. That's the first operation. Then he gets 1 added to him. And so we subtract off the 1 first, right? To give us 2x equals 2. Then we divide by 2 to get x equals 1, right? This is the same kind of thing we're going to be thinking about. Only today, of course, I think you know what this is what we've been heading towards, is we're going to have things like this, things that look like ax minus h squared plus k. And in this case, yes, we have the squared thing, but we talked about how, well, let's do it this way. Sorry, I was getting ahead of myself. But as you can see, this is the goal. This is why we're even bringing this up in the first place, is that we have both addition and subtraction, right? Which, as we've seen, and as we're going to talk about in just a second, it doesn't matter which order you do the addition and subtraction. But now we have a multiplication that comes into play, and that is going to change things, right? We'll get into that in a second. But let's do this. So, long story short, the order matters. Now, what we were doing last time is we were taking the function x squared, looks like this, and let's say that we wanted to shift it. Why there's x. Okay, now let's say that we shift 1 unit right and 1 unit up. Just graphically, I could draw that, right? I could say, okay, you took the original thing, shifted it 1 unit to the right. So now this point right there, my vertex, moved over to 1. And then we move it up 1 unit here to positive 1. Okay, so pull this guy to the right, then push him up, and we end up with this picture right here. Okay, that's my new thing. As a matter of fact, how would you write that? What's the formula for this guy?
Minus 1 squared plus 1.
X minus 1 squared plus 1 would be this function right here. We'll call it f of x. There we go. Yes, exactly. Pretty easy to deal with. This is one of the nice things about this form is like, well, this thing, if I know where that goes, I could easily find a formula for it. And if I wanted to, I can multiply it out and write it in different ways and all that stuff. This is really nice, right? Now, check this out. It didn't matter which way I chose to do this. First I drew the one right here on the x-axis and said, okay, we're going to shift it over to the right. Then we're going to push it up. But I could have done that in the opposite order. I could have said, okay, well, hold on. Let's push up first 1 and then pull it over to positive 1. So up and then right. And we would have ended up with the same picture. I'm imagining that I could actually reach into math land and grab x squared himself, the actual function x squared. I could grab him, move him this way, and then push him up. We'd end up with our new guy, f. And it would look like this. But had I reached into math land and pulled x this way and then pulled it that way, we'd end up with the exact same picture. My point is that when you're adding and subtracting, when you're shifting, when you're translating a function, it doesn't matter what order you do that in. You're gonna get the same thing. Okay, now we're gonna take a break. We're gonna move into new territory, but this conversation we just had will come back into play. So now, what about multiplying? So we've talked about adding and subtracting, right? As a matter of fact, and let's think about this x-axis. This is the input axis. If we're thinking about this thing, x squared, as a function, and now I'm going to call this guy f. X squared is f of x. The input axis is the x-axis. And when we add or subtract to the x-axis, it moves this object to the left or to the right. When I add or subtract to the output, that is when I take the output, whatever it happens to be, and I add or subtract a number, well, I'm adding or subtracting to the output, and so it moves in the output direction. Okay? Now what we're going to talk about today is what happens when we multiply the output by something. We take a number and multiply the outputs. What direction here on the plane do you think this is going to modify? The left-right direction or the up-down direction?
Left-right.
Multiplying the outputs by something.
Up-down.
Up-down. Because think, and this will be obvious when we actually start to do it, but if we wanted to move stuff to the left and to the right, we modified the inputs, right? We modified the x value, right? We said, well, if you change the inputs, if you do something to the input before it even gets there, what that does is shift it along the input axis. We also said if you take the output, whatever the output happens to be, and then you add something to it or subtract something from it, well, then it moves the outputs up and down. And so what we're doing here is today, we are going to look at what happens when you multiply the outputs. The inputs are staying the same, right? We're not going to, for now, we're not going to be doing anything with that. We might briefly look at, we're going to pull up Desmos later, and we're going to see what, it'll be easy to just plug something in and see what does happen when we multiply inputs by something, but that's not really the point of what we want to, sorry, that won't help us with parabolas, really. So, but the outputs now, what we're going to do is we're going to take the output of this function. That is, we're going to take its y value. Remember what that means, right? Like f of x means the output you get after you plug in a number. So let's actually plug in some numbers. I plug in 0 for x, and what do I get out?
0.
Yep. I plug in a 1, and what do I get?
1.
A 1 comes out. I plug in a 2, and what do I get?
4.
A 4 comes out. Now, what did we just do? We just said, look at what we did. In that last case, we said you plug in a 2 and out comes a, and what do you do? Well, that's what you did. You said, well, if the 2 goes in, then 2 goes in and gets squared. And then the 4 pops out. But remember, this 4 is the same thing as this. That is, right, like that's a fancy symbol to say the output that you got, that right there represents the output that you got after you plugged in 2. In other words, this thing right here is we could represent that as f of 2 right there. So, okay, the outputs, we have this output. Now let's say, now we're going to do something like this. We're going to say, we are going to take the output of this function, of x squared, and then after doing that, right, this says do something kind of like earlier, right? I said you have a number, and you chose a number. I said add 1 to it, and you did. Then I said now multiply it by 2. And so then you multiplied it by 2. That's kind of what we're doing here. We're saying we're doing something with a number. In this case, we took 2 and we plugged it in and we got this. Now that you have that, take that and multiply it by a number. And let's make this concrete. Let's say we're taking this and multiplying it by, oh, how about the number 2? Could have been any number I wanted, but what would happen? I claim that this changes the output value. In other words, I say that it's going to change the height of this thing. And let's just take a look. What's this going to do? Well, if I took 2 times f of this original thing, in other words, I took my 2, plugged it in, and then multiplied it by 2, we would have 2 times, well, I took my 2, plugged it in, took 2 squared, gave me 4. There's a 4 right there. What's 2 times 4?
8.
8. So now what I'm doing, what I'm trying to do is draw this function here. 2 f of x, which we could think of as 2 times x squared, right there. And what it just did is I plugged in a 2, and instead of getting 4, I went up to 4, but then I took 4 and multiplied it by 2. And so I didn't draw this very well, but it actually shot it up here to the number 8. It'd be a lot easier if I think about, okay, what happens if I plug in a 1? Let's trace this through. Now we're trying to draw 2 f of x. Right? That's what we wanted. That's what we want. Now let's plug in a 1. So what is 2 times f of 1? First off, what's f of 1?
2.
Just f of 1. What happens when I plug in 1 to my original function?
You get 1.
Yeah, get 1. Okay, cool. Right. Because f of 1 says take 1 squared. And so now we get 1. Now what's 2 times 1?
2.
Just 2. So now this took that number. When I multiplied f by 2, it took the output value and shot it up to 2 right here. Okay. Now you could kind of imagine what's happening. You're taking, because you see what we're doing, right? We're taking the output values of this original function, multiplying them by a number that's bigger than 1. And so if you multiply something by a number that's bigger than 1, it gets bigger, right? And so when you were at 1, your output was 1. We're just saying, take whatever output you had, multiply it by 2, and now it should go up even higher, right? And if we were to continue this on and on, this thing would look like this. Does that make sense? Why the shape got pushed up that way?
Mm-hmm.
Each one of these heights right here, right? Whatever that height is, whatever that output value is, then gets multiplied by 2. And so if it's at 2, it goes up to 4, right? If it was at 2, it went up to 4. If it was at 1, it went up to 2. If it was at 9, it would get multiplied up to 9 times 2 is 18. Yeah, 18. And so, okay, what are we doing here? So when I have a number times x squared, if that number is bigger than 1, well, if it is 1, you just have x squared, right? Like, let's go over that obvious case right there. What we're trying to do is we want to get our minds around what happens when you take some number times the output of a function. The function that we really care about is x squared. And so we're saying, okay, when you do that right there, that's going to stretch, and that's what we actually call it. We call it, it's going to stretch the outputs. It's going to stretch in the vertical direction when a is bigger than 1. So when a is bigger than 1, actually, I'd rather do it this way. I'm sorry. When 1 is less than a, then this is a vertical stretch. I think I spelled stretch right, but I could write it really ugly with like doctor handwriting, so I could play it off if I didn't. Okay. So again, let's think about how we would compute something like this. If I just told you a x squared, and I gave you a bunch of different values for like we wanted to plot this guy, right? I'd say, okay, when I plug in a 0, I get 0 squared. Well, times a, I guess, is just 0. Okay. Plug in a 1, I get 1 squared is 1 times, well, whatever a is, I guess, right? And so we're up here at a. Plug in a 2, okay, I get 2 squared is 4 times whatever a is. You can see, like, when a is big, like when it's 2, you're up here at 2, and then it jumps up to 8, and so on and so forth. The point is that this thing, basically, from the original x squared, that's my original x squared, every point gets shifted upwards. And we call this a vertical stretch right there. This will look really nice when we go to Desmos in a few, right? But it's a vertical stretch. It stretches it upwards. Does that make sense? Do you believe that?
Yes.
Okay, so now let's see what happens when we multiply by a number where a is between 0 and 1. Because if you take any number, like when I said at the very beginning of class today, take a number, and you took a number, and then I said multiply it by 2, of course it got bigger, right? I don't care what number you started with, unless you started with 0. That makes sense. 0 didn't move, did it? Interesting. 0 times anything just stays put. Okay, that might be handy later. But anyway, any number that's not 0, when you take it and multiply it by a number that's bigger than 1, it grows in size. If you started with -3 and you multiplied it by 2, you'd have -6, still bigger, right? It's like, yes, it's more negative, but it's still a bigger number, like an absolute value, right? But anyway, right now we're just going to be talking about positive numbers because that's what we care about. We care about what happens when we multiply the function x squared by some number. So in other words, we have the output x squared, we have this nice parabola, and we want to see how does its shape change when we multiply the outputs by different numbers. And when a is bigger than 1, it gets bigger. All the outputs get larger. And so it has this effect of stretching the original function upwards. Okay. When a is equal to 1, you're right where you started. You haven't changed any of the points. It's still just x squared. So now let's take a look at what happens when it's between 0 and 1. So to be to make this concrete, let's do an actual example of that. we're going to start with, and actually I'm going to do it this way. I'm going to put a bond. Here's my original function, x squared. I plug in a 0, I get out a 0. I plug in a 1, and I get out a 1. I plug in a 2. Let's make this a little bit like that. Plug in a 2, and I get out a 4. Okay, so that's, it looks terrible. That's the function x squared. So now let's take that function x squared, and we're going to multiply it by some number between 0 and 1. Let's go halfway. How about 1/2? Let's multiply it by 1/2, and let's see what happens. If I take 1/2 f of x, let's see what that does. That's the same as 1/2 times x squared. So if I plug in a 1, I get out a 1, but then I multiply it by 1/2. So what happened? What do I get? What's 1 times 1/2?
1/2.
1/2, right? And so, okay, that would be, now I am graphing this function right here. That's what I'm trying to do. As a matter of fact, I hate that I got these brand new markers and they all look terrible. They just look so bad. Let's see if red. Can you see red? Can you see that red right there?
Yeah.
Oh, good, good, good. Okay, so let's plot these in red. Okay, so we took 1, plugged it in, and we got 1 squared. Cool. Then we multiplied it by 1/2. Okay, so then the output of this function would be 1/2. Okay. Now, let's plug in 2. I plug in 2 for x, and I get 2 squared is 4. Then I multiply that by 1/2, and what do I get?
Two.
2. 1/2 of 4 is 2. Okay, so we go to 2, and it actually pops me up to 2. So there's that 2 right there. And we can kind of see what's happening, right? Every point that you had on your original function, x squared, we take it and we just take 1/2 of whatever that was. So it has the effect of dropping these points down by a factor of 1/2. And if we continued this process on and on and on for all of the other points, we would see that it does this kind of thing. You take whatever value that is, you take 1/2 of that value and it just drops it down, right? Take any number, take 8 and multiply it by a number that's smaller than 1, between 1 and 0, and it should make that number smaller, right? Like take 8, multiply it by 1/2. What just happened? Well, you just halved it. You took it and brought it down by 1/2. That's going to happen whenever your number is less than 1 and bigger than 0. All of these points, every single output value, because remember, that's what this black cup represents. That parabola is the original x squared. So we're going to take all of those heights, each one of those heights, the output values, take that and then multiply it by 1/2. Well, that's going to have the effect of dividing it in 2. We're going to, and every single point is going to have to come down like that. And so what we call this, it's a change in the vertical direction, but we call it, instead of a stretch, we call it a compression. So when you multiply, we're building this up right here. That's what we're doing. We're saying what happens to this original function when you multiply the output by a number. Well, if that number is bigger than 1, it stretches it out. If that number is between 0 and 1, it compresses it. So we call this a vertical compression. It compresses it vertically or whatever. And so, okay, we have when the number you're multiplying, so does that make sense? Why it does that, why it has that new shape that it has?
Yeah.
Okay. I'm just to be complete, I'm going to cover this. If you multiply it by 0, it's going to be 0. Like there's no way out of that. Like if you take a number, multiply it by 0, it just goes away. It always goes down to 0. There's no way out of that. So we're not gonna, and then you don't really have a graph of anything. If everything's 0, it's just 0. And we're not gonna talk about that. It's just, that's obvious. Okay, so we've talked about when the number you're multiplying by is bigger than 1. We talked about when it's between 1 and 0, what happens. Now let's talk about what happens when it's negative. And let's start with what happens with just -1. So I'm gonna erase some stuff here. You got all this stuff. This makes sense what I drew very, very poorly.
Yeah.
Yeah, okay. All right, now. Just remember the name of this game. Like we've already done this. We're kind of approaching this from the front, right? We're going to see, let's suppose we have a function and we want to take it and shift it around and what happens when we do that. But really, and we could see from the homework, like why this is nice, because we could play the backwards game. We could say, well, hold up, this function that I'm looking at, we could think about this as just taking some function that I knew and shifting it, right? Like in the homework, we had stuff like equals x squared plus 2x minus 1. And we said, man, I don't know what that thing looks like. But then we were able to do stuff like this and say, well, hold up, if I complete the square, I go plus 1 squared minus 1 squared. Then I end up with this is x plus 1 quantity squared minus 1 minus 1. So this original function is actually, we can write it like this. And we could say, like, it could have been given this way. But it's like, what we're developing here is kind of, we're going the backwards way, right? It's like, the way that you usually care about all this stuff that we're talking about is that you have something like this. And it's like, what does that look like? How could I draw that kind of thing? It might really help me to draw it out. And so that's what we're building up right now is like, if we could break this into steps, right? If we could say, well, wait a second. We know that if you move a parabola this way, it's the same thing as doing this kind of thing. We know that if you move a parabola this way, it's the same as doing this kind of thing. Therefore, this thing that we're talking about, now we're kind of going in the backwards direction. It's like, oh, we can realize this as my original parabola, x squared, that has been shifted to the left 1 unit and down 2 units. And that's nice, right? The only thing that's missing from this puzzle is what if you had something out here in front, right? If you had some value in the out here, we want to see what that does to the thing. So just wanted to keep all this in mind. You tracking? You feeling good with where we're going here?
Yeah.
Okay. So then we're saying, okay, this is if you multiply the output by a number bigger than 1, it stretches it up. If you multiply by a number that's between 0 and 1, it compresses it down. Now we got to deal with negative numbers. Okay, so let's do that. We have our original function, x squared. And let's take the easiest negative. Well, first off, okay, sorry. Let's get some points on this guy. Let's plug in a 1 and we get out a 1. Plug in a 2, we get out a 4. That's also what happens when you plug in a -2. The 1 is also what happens when you plug in a -4. So we have this nice bit. And so, all right, let's just look at what happens. I've drawn 5 points on here, and I think you know how I got them. I plugged in a 0 into that function, x squared. 0 squared is still 0, so it didn't move, it stayed put. Plugged in a 1 squared, still 1, and it stayed put, but we're gonna put it right there, okay? Plug in a 2, squared it, we got out a 4. Okay, now what we want to do is see what happens when we take our original function, f of x, and we multiply it by -1. So what I'm going to do is say, okay, so in other words, what we're trying to draw is the function -1 times f of x. Well, that's the same thing as -1 times x squared. Okay, or we could think about it as negative x squared at any rate. What this says to do is you plug in your x, you take your favorite x, I'll take 0, plug him in right there. I get 0 squared is 0 times -1. Well, it's still 0. It hasn't changed, right? So -1 times f of 0, same thing as -1 times 0 squared. -1 times 0 squared is 0. -1 times 0 is just 0. So he didn't move. He stayed put right here at 0. Okay. Okay, now you do 1. Let's plug in 1 into this new beast that we have over here, and you tell me, what do I get? In other words, what is -1 times f of 1?
-1.
It's -1. Why? What is f? Well, first off, what is f of 1?
1.
1, right? The output, right? Let's not lose sight of what that symbol means. It means you took a number, you plugged it in, and you got a new number out. That new number that you got out was 1, okay? We take 1 times -1, it gives me -1. Okay, so this new function that I'm trying to graph here, it says instead of being up here at +1, we're just down here at -1. So I plug in a 1 and I get out a -1. Okay, let's do another one. What happens when I plug in a 2? What do we get?
-4.
-4, right? Because -1 times f of 2. F of 2, I plug in a 2 and it tells me to square 2. So I square 2 and I get a 4. And so then f of 2 is the same, the output of f of 2 is 4. And so then I simply take that and multiply it by -1 and I get a -4. Okay. And so it drops it way down to here to, oh man, I drew that all crooked. Drops it down here to -4 right there. And do you believe that every other number in between here is just going to get mapped exactly? I'm not stretching it at all. It's just a 1, but it's just making that number negative. If my output was 4, it becomes -4. If my output was 1, it becomes -1. If my output was +1/2, it's going to drop down to -1/2. If my output was, I don't know, 3, it's going to drop it down to -3. And I'm going to end up with this right here. What about that side? Well, your output was +1. And so you multiply it by -1, it's just going to drop it down to -1. What about this point? Where does it get mapped? This point here at -2, 4.
1 second. Okay. Negative what? 2?
Yeah, you take a -2.
-4.
Yeah, you get the +4, and it just drops it down to -4. It's one of the easiest things we could do, actually. It's taking the outputs of a function, multiplying it by -1, it reflects it over the x-axis. this is kind of nice because we're starting with a point that's 0 right here. So it's really easy to see, like if I just took this guy and flipped him over, right? Flipped it over this x-axis, we would have exactly the picture that we're looking for. And so, sorry, he just got my attention. So, okay, negatives, they simply just take your outputs, flip them over the x-axis. In fact, I'm going to call this is going to be a special one. When A is actually equal to -1, we're going to call this a reflection. Because you can imagine, right? That's like if you imagine you had a mirror and you set it down right here on the x-axis like that, then that would be a mirror reflection of that. That's, here we go. It's a reflection, and we call that about the x-axis. When A is equal to -1. What's nice is now we know exactly for all of the other numbers. Because if we have, say, -2, right? If we wanted to know what happens when we have I hope green works. Please work green. I want this to work. So let's say we wanted to know what happens when you multiply f of x by -2. We could say, well, wait a second. This is the same thing as taking this right here. We could say it's the same thing as first multiplying it by 2. Multiplying the output by 2, which does what? Well, that would be a vertical stretch. As a matter of fact, we've done that already. It would be like saying, first stretch it up like that. Right? Stretch it up by a factor of 2, and then make it negative, right? Then make it negative, which would be a reflection about the x-axis. So you take whatever picture you just drew. This would be the 2f of x right here in green. Then we make it negative like that, and we could say, that's what it would do. It would bring it down like this. And this would be -2f of x right there. Now, yet another way we could have done this is just plug in a bunch of numbers. But again, we don't want to do this point by point. We want to see kind of the global picture of what's going on. We don't need to do a bunch of different points, but I'm going to do that just to prove or to kind of suggest that this would be the same thing. If I took -2 times f of something, well, let's just see, f of how about 1, that would be the same thing as -2 times f of 1 is 1 squared. 1 squared is 1. So -2 times 1 would be -2. So it's kind of the same thing as saying, okay, you go to 1, you get 1, then you've multiplied it by 2 to get 2 right there. But then you make it negative. So it flips it down, it reflects it across the x-axis, or reflects it about the x-axis down here to -2. And if you want, you could go through and find a whole bunch of different points, but this is kind of a nice way of thinking about it, right? If it's negative, it flips it. And if the number is bigger, right, in absolute value, if it's bigger than 1, then it stretches it vertically. It's still a vertical stretch, it just happens to be stretched down. Similarly, if I had started with, say, instead of this, so I just went ahead and erased that. Were you ready to roll?
Yeah.
Okay. Similarly, I could say Okay, if it were a negative 1/2 f of x, you could say, well, that's the same thing as negative 1 times 1/2 f of x. I know what 1/2 f of x does. 1/2 is a number that's between 0 and 1. So that's going to take all of those output values here on f, and it's going to compress them down by a factor of 2. And so it's going to compress it that way. But then you just take it and make it negative. In other words, you flip it about the x-axis, and it's going to come down and look something like this. So let's kind of make this complete. Let's do that with f of 1. We take f of 1. You take 1 and square it. 1 squared is 1. So this is kind of this first part here. We're taking 1, plug it in, and we got 1, but then we divided it by 2. So multiplying it by 1/2 brought that guy down to 1/2, right? It compressed the output value. But then we took whatever that was, which happened to be 1/2. That was my new output back up here. And then we just said, well, now just flip it across the x-axis, rotate that guy around. And so he ended up right here at, what do you know, negative 1/2, just like that. And so we could, if we wanted to, we could continue this on and say, I'll make a little bit of room. Do you need this anymore?
No.
Okay, so I did not, well, I thought I had enough room. I would have written this down beneath, but I did not. We could complete this and say that then between negative 1 and 0, this gives you a vertical compression and a reflection about the x-axis. I'm not going to write about the x-axis. We could see why that was the case, right? Multiplying by negative 1/2, that's what this was, negative 1/2 f of x. This guy was 1/2 f of x. Kind of like the same thing. And I actually think it's easier to do this here. Like if I'm trying to figure out what does negative 2 f of x look like, I say, well, what does 2 f of x do? Well, 2 is bigger than 1, so it stretches it up. It takes all the output values and shoots them up by a factor of 2. Then since you're making it negative, you just take all those values and flip them down. And so now you have that. Okay, good deal. So it ends up being a vertical. Yes. Sorry. Yes. So when it's between negative 1 and 0, right, then it is a vertical compression and a reflection. The last thing is when a is less than negative 1. In other words, something like negative 2 or negative 5 or negative 88, right? It's going to stretch it because the number is bigger than 1. But then that negative is going to flip it. And so this will be a vertical stretch and a reflection. Is all of that making sense? Do you have any questions about that stuff?
I don't think so.
Okay, this will make a lot more sense. Now, this is kind of, having it like this is kind of a pain to deal with. It's easy when you see, oh yeah, there's an actual number 2 there, you know, like, but to have it organized like this is just to make things complete, right? Like, I don't expect that you're going to like memorize like, oh, wait a minute. Okay, if I have ax squared and the a is between this and this is just to have this written down somewhere. What we do is honestly, you're given something like this. What is negative 2 f of x look like? Well, -2, well, first off, 2 is big. So you're stretching the outputs. Negative flips it. And so you're not really referring back to, oh, wait, which case is this? Well, a is between here. Oh, and so it's this. I'm just having this so that we have it written down somewhere, just in case we need to like triple check ourselves. But let's look at Desmos, and this will make our lives a lot easier, I think. Okay, so, oh, actually, before I do this, would you turn off your video? Because I can, in the past, I've been able to put a little black box over your face because your face pops up on here. It's way easier if I don't have to do that. It just saves me some time. So, okay, right now we are plotting this. I'm going to move this over a little bit. Okay, so our original function, f of x, is x squared, which is our old friend that we've been working with, right? Let's just check. Plug in a 1, we get out a 1, okay? Plug in a 2 on the x-axis, and we get out a 4 on the y-axis. Can you see my cursor when I do this?
Yeah.
Okay, cool. Otherwise, I wouldn't bother. But yeah, okay, so we get out a 4. Now, you don't see it says that it's being plotted in blue, but you don't see it because I've overlaid it with G. Let me get rid of G. So we just believe like, yes, F is sitting there. F is the blue function, x squared. Now what we're going to do is plot a times x squared. I could have written this as a times f of x. If you remember, we did that before. And one more thing, you could see that a is equal to 1 because the slider right here that gives us the value of a is set to 1. So right now we're just plotting 1 times x squared, which is just x squared. Just to be complete, we could have said plot h of x equal to a times f of x. And you could see like, yes, we get the exact same thing. This that I just wrote a times f of x is exactly the same thing as a times x squared. We're not going to do that. We're just going to look at it like this. Okay, now we're at 1. So let's take a look at what happens when we bring a up to 2. This is like the first example we did in class. When we take our outputs and multiply them all by 2, what happens? Well, the function gets, all the outputs get stretched vertically by a factor of 2. We were at 1 here on the blue function, 1, 1. You plug in a 1, you get out a 1. Now it says you plug in 1, get out a 1, then multiply it by 2. And we're up here at 2. Used to be the case that we plug in a 2 and we get out a 4. But now it says, well, whatever the output was, you take that number 4 and then multiply it by 2. And so what happened? Well, it got shot all the way up here to 8 because 4 times 2 is 8. Okay, so all right, that looks nice. That's what we expect. And another thing we could do, if we're so inclined, we could keep stretching this as much as we want, right? If we make it bigger and bigger, it just keeps stretching it more and more. Like when a is equal to 5, used to be the case, plug in a 1, we square it, and we get out a 1. Now it says, plug in a 1, square it, you get out a 1, then take 1 and multiply it by 5. And so he got stretched all the way up to 5 up here. Ditto with 2. It used to be you take a 2, plug it in, you get out a 4. Now it says take a 2, plug it in, get out a 4, then multiply it by 5, and we should be way up here at 20 or something. Yes, finally, way up here at 20. Plug in a 2, you can see where the 2 was. It's along this line, plug it in, and you get out a 20. Okay, so now let's put this all together. So that's what happens when you multiply by something that is bigger than 1. It stretches it up. Or I should say, stretches it vertically. It stretches the function in the vertical direction. And so then, okay, the next thing we talked about was what happens when you have a number between 0 and 1. Well, what you're doing is you're taking all your output values, multiplying them by a smaller number. In effect, you're making all of them smaller. You're squashing them down, right? And so we did 0.5 or 1/2 is what we did earlier. Let's zoom in a little bit and just see. Yeah. So it used to be the case that I plug in a 1, I square it, and I get out a 1. And so that height of 1 is my output value. But this says you take that, multiply it by 0.5 or multiply it by 1/2, and it drops it down to 1/2. Used to be the case that I plug in a 2 and I get out a 4 because 2 squared is 4. This new function says, well, you take 2, you square it, you get 4, but then you multiply it by 0.5 or you multiply it by 1/2. That drops it down from 4 to 2. And so that's the picture we end up with right there. We keep going down and down. We get smaller and smaller numbers. It keeps compressing this graph. This is why we call this a vertical compression, because it's as though you took your blue function and you compressed it, right? You pushed it down towards the x-axis. It compresses it in that direction until we get, oh, we jumped right into it. 0.1 compresses it even more. Finally, at 0, what did I say? It's like the most boring function. It's just always 0. Nothing happens, right? It's just 0. Hey, what is it when you plug in a 20? It's still 0. Nothing has changed. Now let's see what happens when we go. Let's just jump right to -1. All right, there's -1. It's exactly a reflection across, or I'm sorry, a reflection about the x-axis. Let's get some numbers here. Okay. Used to be plug in a 1, you get out a 1. Well, this says just take that output and multiply it by -1. In other words, flip it, make it negative. So it jumps down to -1. Ditto with 2. You plug in a 2, you get out a 2 squared, which is a 4. Then you make it negative. It reflects it exactly 4 units down, right? Whatever the height was, it just gets reversed. It just goes down below. That's why we have this nice reflection. If we drag A to a number lower than -1, like to -2, this is the same thing as if we had, and I'll do this real quick. So it's as though we took x squared, multiplied it by 2, and then reflected it about the x-axis. So let's think about that, right? Used to be that we'd plug in a 1, we'd get out a 1 as my output. But then this 2x says, well, you take your output, multiply it by 2. So it gets stretched up by a factor of 2. Now, finally, in G, we're saying, whoa, it's not just 2, it's -2. So it's as though you stretched it by a factor of 2, and then you reflected it down here to -2. And you can see that the red and the green functions are exactly reflections of each other, right? Like up here we're at 2 and 8 with the red function, because when you plug in a 2, you square it, you get 4, then you multiply it by 2. And so the red function says the output is 8. But in our function g of x, it says, well, it's -2 that we're multiplying by. So you did all that. And then finally, you went and you reflected it down to -8. And so I think, so you could see what happens. It continues to stretch if you go way down, and it goes up if you do this. So this is what you're doing as you vary A. That is what that guy looks like. Is this making sense?
Yeah.
Does this visual help? I think it does. I love
Yes,
having.
it does. I love Desmond.
Yeah, I know. I do too. I do too. It's really cool. So, just to be complete here. Oh man, like I wouldn't even take notes on this because if and when we get to this stuff again, we'll go into it in more depth. But what we've talked about so far is what happens when you multiply the output of a function. We have not talked about what happens when you multiply the input of a function. And just real quick, let's do that. So one more thing I want to do, actually, before we do that, we're going to say, how about x? Minus 3 squared. How about plus 1? Okay. Now, bring this guy down to 1. Now, remember at the beginning of the class, when I said that it matters what order you do things when you're mixing addition and subtraction. Okay. Let's see what happens. So right now, the green function is the original f function, but we've just taken it and multiplied it by, well, 1. So it's exactly the same. So now let's see what happens when we multiply that entire function by a number that's bigger than 1. What's it going to do? Oh, it doesn't just stretch it. It pushes it up. Why is that? Well, because we're taking the entire output, every single output number. Like, for instance, we're taking here at 3. So into the blue function, we plug in a 3. And it says, okay, you take x minus 3. So 3 minus 3 would be 0. You square it, you get 0. Then you plus 1. And what do you know? You end up here at the output is 1. What the green function says to do is you take that output and then you multiply it by 4. And so the entire thing ended up getting shifted upwards. So that's the whole thing being shifted upwards. In other words, what I've graphed here with G is this. It is the function 4 x minus 3 quantity squared plus 4 times 1. And yes, that blue function ended up right above the other one. Right? I mean, it ended up right on top of the green function. As you can see, I'm flipping them off and on, right? Now that's different. That's a different beast than if we had something like this. What about just 4 times x minus 3 squared? And then we simply add 1. Yeah, that is completely different. And so my point here is that with what we're doing, I guess what I want to say is that we are concerned with this type of thing because right now in class what we're talking about are parabolas. And we know that every single parabola can be written in that form, a times some quantity squared plus some other thing. And so what we're dealing with, what we want to mess with is just what happens when we multiply a parabola that's been shifted left or right by 1. Not a parabola that's, when we multiply the output of something that has first been shifted left or right. Here, just to be sure, I'm going to get out of here for just a second. Okay. So what I'm saying is since this is the type of thing we care about, ax minus h squared plus k, we could see that, well, this right here is the same thing as just taking a parabola and shifting it left or right along the axis. If you think about the order of all of this, and this is where this all comes back into play, this says, well, if we think about what happens to x, the first thing that happens to x is he gets shifted left or right. Then he turns into a parabola. So you've taken or we can think about this as all one step, right? That a parabola gets shifted over to wherever h is. And now we have this parabola. So this thing right there is x minus h quantity squared. Since that's the case, and this is the type of thing we care about, then this is really the only, at this point, this will be sufficient, this case that we're studying. In other words, what happens when your vertex is still on the x-axis and then you multiply it by something? Remember earlier when I said, no matter what, like when you multiply this, that 0 is going to stay put. And we saw that in Desmos. We saw that when we did these examples. And we can see that by, if your output is 0 and you multiply 0 by anything, it ain't going to move, right? So then when you go and do this, then you multiply it by a, all that's going to do is stretch it. It's going to stretch it, but it's going to keep it in place. Okay. And so, okay, there's the a right there. That's the a x minus h quantity squared. And then the final thing we do is shift it by k. And let's say that k is a positive number, so it actually shifts up. And so the thing that we end up with is this parabola, which would be our final thing. I'm sorry, this looks so ugly. That would be a x minus h squared plus k. So we could figure all that stuff out. And so we have a shift, which is which is addition and subtraction. Then we multiply, which does some kind of stretch. Then we add. That's different than if you did all of the stretching first, which, let me go back to Desmos. This is what I was trying to illustrate here. So here at the bottom in blue, or I'm sorry, the green one right here that I'm scrolling over. This one says you shift over to the right by 3 units. Then you do your stretching, then you add 1, and you end up right here where this guy is. On the other hand, what this thing is right here, this is the same as this g of x. Yeah, it is. Those are the same guy right there. As you can see, as they blink off and on, they are the same. They're the same guy. This says you do your shift. You do your shift left. You do your shift up, because that's this F right here. You shift to the right 3 units. You shift up 1 unit. Then you multiply everything by 4. That is a different beast. And luckily, thankfully, this is not the kind of beast we are going to be dealing with. We don't have to worry about what that does. Long story short, don't worry about that guy or that guy. So I wanted you to see that, because this will come into play before too long. It's something that we have to be careful of. But what's nice with parabolas is that this order is always the same. You could always think about it as a shift right or left first, then a stretch, and then finally an up or a down motion. And if you do it that way, then you're not going to have any problems. So Yeah, I think we're done with decimals right now. So, okay, putting all this together. Okay, can I get rid of all this stuff?
Yeah.
Okay. So the point was from the very beginning, the order matters. The nice thing is with what we're doing with parabolas right now, we don't really need to use our brains because this, in the same way that we solve for parabolas in a certain way, right? Like if we have this right here, we'd say, well, the first thing that happens is he gets minus by h. Then he gets squared, then he gets multiplied, then he gets added. And that is how we go and solve for this guy. We just do that in reverse order. I'm not going to go through that because we've done that so many times now. And I can see from your homework, you have no problem doing that. You get that. Well, the same thing is true with the shifts and the stretches and the compressions is we could do that in that same order. We could say, well, this thing means you shift right h units. And yes, it's a parabola. We know that. Or you could say, then you square it. Yeah, but the thing is a parabola that you've just shifted. Then you stretch or compress or reflect by A. Then you finally shift him up and down. And that's kind of nice because then that takes a lot of the guesswork out. As long as you do it in that order every time, yes, the order matters, but as long as you do it in that order every time, you're not going to mess this up. So let's finally get to an example. And this is what your homework is going to look like. So I wanted to do minus 3x squared. We're going to go plus 6x. And we're going to make it easy with a plus 1. We want to graph this guy. And in fact, we want to answer all the same questions that we did last time, like for your last homework. And so first off, we got to complete the square. So I'm going to do that real quick. Let's see. Step 1, copy this guy down by bringing that guy over. Okay, now I'm going to factor out the leading term. I'm factoring out a -3. And so what happens to everything that's in here? I'll give you a hint. The first one is x squared. Then what do I have left over?
Minus 3x. 2. No. 2x.
Minus 2x. And of course, every single time I write something down, I check it. So I'm going to go big. Then -3 comes in, gives me a minus 3x squared. Yep. -3 comes in, minus is positive. 2 times 3 is 6. Yep. Okay, we're good to go. Now, I'm going to say, well, I'm going to take whatever half of that guy is. And so what's half of 2?
1.
Okay, so I'm going to go plus 1 squared minus 1 squared. Why did I do that? Well, because the only way to turn this thing into a perfect square is if that is half of that squared, or if that is half of that squared, which that is now. And so, okay, then this becomes what squared minus 1 squared?
X plus 1 squared.
Plus?
No, sorry, minus 1.
Ah, good. X minus 1 squared. Now I'm going to check that because I could FOIL these out real quick. I know first outer inner last first gives me x squared. Outer inner, of course, is the same. So it's -1 is a -2. So minus 2x. Good. Last is a negative times a negative is a positive 1 squared. Yep. And then you have that right there. So yes, those 3 terms are the same as that guy. That one term is the same as that guy. So we haven't changed anything. Now, here comes the really tricky part. In fact, I'm going to make this a little bit easier by I'm going to go ahead and square 1. 1 squared is still 1. Okay. Now, notice that was not plus -1 squared. No, that was minus, because you've done plenty of these now, and I think you get this now. It's always going to be minus. Always going to be minus that's sticking out here because the plus thing went into here. The minus thing, it's always going to be minus. So, okay. I have to distribute that -3. And so the -3 comes into here to give me this. And then what happens here? What am I left with in there?
0.
Wait,
Oh, I guess -3. Sorry. Wait, plus 3.
+3. +3, and then I drop parentheses. That's why that's so important. And using parentheses will help you every single time. Okay, so I do that. Now that I've distributed, I can drop parentheses and finally put everybody together. So this is a -3, x minus 1 squared. How about well, 3 plus 1 is 4. So how about +4? Okay, so part 1 is done. I've completed the square to rewrite this in vertex form. So by the way, I don't think I've ever said that. I believe most authors call this vertex form. Why? Well, because that's the vertex right there. Yeah, okay, so. Okay, now we need to describe the shifts and the stretches. So what's the first thing that happens? Look at X.
Yeah.
X, and then tell yourself, like if you plugged in, say, a 7 for X, how would you go about calculating that? What's the first thing you would do?
Subtract 1.
Okay, so what does that mean geometrically? What is that?
It means go right 1 unit.
There we go. So this is a shift right 1 unit. Then what happens to it?
It gets squared.
Well, yes, that's true. It does. So therefore, we're dealing with a parabola. You kind of think about this as you just have
I see.
Yeah.
Okay.
And so yes, then it gets squared, which means, okay, the thing that you just shifted was X squared. So yes. Then what happens to X?
It gets multiplied by -3.
Aha. And so is this bigger than, in absolute value, is this bigger than 1?
Yes.
Yes. So is this a stretch or a compression?
Stretch.
And so what we're going to do, we didn't talk about horizontal stretches. There are horizontal stretches, but we haven't talked about them. So this is a vertical stretch. Vertical stretch. And then what we usually do is say by a factor of 3. So we'll say vertical stretch by a factor of 3. Okay, and if it happened to be something like this, like let's say we did this, right? And you'd say, okay, well, first it's a shift right 1 unit. And then now, is this a compression or a stretch?
Compression.
Compression, because 1/4 is smaller than 1, right? In absolute value, it's smaller than 1. And so it's going to take all of your output values and squash them down by a factor of 4. This always messes me up. I'm like, wait, a compression by a factor of 4. So if somebody told me a compression by a factor of 4, so I don't care if you call it a compression by a factor of 4 or by a factor of 1/4 or whatever, just whatever. I'll know what you mean. You know what you mean. We're not going to nitpick about this, whether this is a compression by a factor of 4. I think technically that's what it is. You compress something by a factor of 4 means to divide by 4. So then, but you see, now that's a pain, because then what if it's 3/4? Is it a compression by the factor of 4/3? I guess, and that's just a pain. So however you want to say it, whatever, what I'm going to be looking for is vertical stretch or compression, and then by a factor of, and then you call it whatever you want. I'll get it. I'll understand. Okay, so that took care of the absolute value of this guy, but he's negative. So what does that mean? What does multiplying by -1 do
Flip.
to the graph?
Flip.
Reflection, then it's a reflection about what axis?
The x-axis.
Did you say the x-axis?
Yes.
Good. About the x-axis. Okay, that's a reflection about the x-axis. So, okay. The -1 shifted it by 1 unit. The squared means that the thing you're shifting is a parabola. Then we multiplied by -3, which did these two things. Okay. Finally, what's the last thing that happens here?
It is shifted up 4 units.
There we go. Shift up 4 units. Okay. So the rest of this we know how to do, but I would like to do this real quick. So we took our original parabola, our original x squared. It looks like this. We shifted it right by 1 unit. Okay, so we shifted it to here 1 unit, and it's still our original parabola. It looks like this. Okay, then we stretched it vertically by a factor of 3. Okay, so now it looks like this. It got skinnier, right? Or it got pushed upwards. Then we reflected it about the x-axis. So this thing then got skinnier, but now he's reflected about the x-axis. Finally, he got shifted up 4 units. And so this whole thing got shifted up 4 units. And now I still don't know, does it go through like that? Is it so skinny that it goes through right here? Does it? Well, that's where, but I have a general idea of what it's going to look like. Now, for the ins and outs, like, does it go through over here? What does it do? Well, actually, I could tell right now, if I plug in a 0 for X, I get an output as a 1. And so, yeah, I could already tell that that's going to look like that. But I'm not going to draw this until I get everything else out, right? Because we have a few other things to figure out. We want to know what's the y-intercept. The y-intercept is too easy to find. So first off, that's the general idea that's going on in my head. So I kind of have an idea of what my final answer should look like. I'm going to say, okay, for the y-intercept, to find my y-intercept, I'm going to set x equal to 0. And as you saw in the homework, it's super easy to just use the original one because, well, you get a 0 plus a 0 plus whatever that thing is. We still call it the y-intercept, even though we're not dealing with a line anymore. It's still called the y-intercept because it's where it intercepts the y-axis. And so we can say, okay, then the y-intercept is equal to y equals 1. Okay, so that's that guy right there. Now I have an idea of what this looks like. The only thing left to do is to solve this guy or set it equal to 0 to find the x-intercepts. So let's do that right here. I kind of want to keep that picture because that's the picture that's going on in my mind. I took a thing, I shifted it, I stretched it up, I flipped it down, and then I pushed them up, and I ended up with that blue guy. Now I just need to find where are these 2 points that, and I could tell that there are 2 points. In the homework, right, like you could tell that when your parabola was up here, you weren't going to have x-intercepts, right? And sure enough, when you solve those, you saw, oh, I have a complex number. This is not on the plane here. This is there. So anyway, okay. So real quick, we're going to find the x-intercepts by setting y equal to 0. So x-intercepts mean to solve f of x, or the output values, are equal to 0. So we're going to do that. Minus 3x minus 1 squared plus 4 equals 0. And I'm thinking, okay, I should not get complex numbers because I could see that this thing does go through the x-axis. And at first, I'm a little scared because when I subtract 4 from both sides, it's like, uh-oh, I'm gonna get complex numbers. But then I go, oh, wait, divide by 3. Let's divide both sides by -3. And when I divide by -3, this guy gets nice. So I get this right here. That's a positive 4/3. Take the square root of both sides. And I get a plus or minus square root of 4/3. Which I could write as 2 over the square root of 3. I think I'll actually do that. That's plus or minus 2 over the square root of 3. Finally, I'm going to bring that 1 to the other side and get 1 plus or minus, because I added 1, right? That brought it over as a positive 1, plus or minus 2 root 3. So that means, and I could kind of see, like, yeah, the 1 plus something will definitely be over here on the positive side. And 2 over the square root of 3 is that, well, it sure looks like it's going to be negative, because if that, I know that it goes through here at 1, right? We did that earlier. The y-intercept is 1. So the only way is that that guy shows up on the negative side. So I'm guessing, and I should be right, that 1 minus 2 over root 3 is the negative number. 1 plus 2 over root 3 is the positive number. My vertex is what?
4.
Well, 2 numbers for a vertex, the x number and the y number.
Right. 1 and 4.
1 and 4. You notice something here? We're going to talk about this next time, but pay attention in your homework. You'll notice that that has something to do with your vertex every single time. If you write it like this, it's always has something to do with vertex. We're going to talk about that next time. So I'm sorry we ran so far over, and we didn't even get into some of the stuff I wanted to get into, but none of that stuff really mattered. I just wanted to show you what happened when you multiply inputs, but we'll get back to that eventually. So does this make sense? It's really the same thing you've been doing. The only difference now is that we have to do this in order, otherwise it could get really jacked up. And so as long as we keep it in the order that we do our right left shift first, figure out what the multiplication does. That's either going to be a compression or a stretch and or a reflection. After that, we're shifting a certain number of units, and that's it. Everything else is exactly the same. So you feel good right now about all this?
Yes.
Okay.